Hello everyone, my name is Jordi Sanchez Riera and I will present the paper entitled Integrated Human Body MoCaps into Blender using RGB Images. First we will describe the different mocap systems and the applications. Then I will present the mocap integration into Blender with the two steps. First we do the transformation from the RGB images to the 3D body joints, and then how these body joints are transferred to the 3D human model. Finally, we'll present some results with synthetic and real data. The first mocap studio started from the movies and video games. They have the big room with several cameras with the infrared lights, and then the actor just put some suit with some markers. These infrared lights reflect to the markers, and then the multi-camera system can detect these reflections and compose the motion. These kind of systems, they need the dedicated space and multiple cameras, so it makes it quite expensive. Also, the actor needs to wear a suit with markers, and the data generated is, the amount of data generated is very big, so this data needs to be processed. In the advantage is the quality of the motion is very high. More recently, we have different other mocap system. It's based with the suit. The suit already have incorporated markers that transmit some signals, so we don't need the cameras to detect the reflections. This makes the system more cheap. Also, it can be used outdoors, and the quality of the motion recordings is still very high. Another advantage is it usually comes with some software that you just put the suit, and the software already can mimic the motion in the model. Another mocap systems are based on the RGB and DEF devices. These kind of mocap systems, the quality of the motion is more unstable, so we have more jittering. Other disadvantages because of this depth sensor, the actions. The actor needs to be not very close, but not very far from the camera. And usually because this camera is a Kinect device, the libraries and the APIs to program this camera, it comes from the Windows or operating system. But the one advantage is very cheap. The advantage is we can find the commercial versions, or we can find also the free versions. Now I will present how we do our mocap system integration into Blender. First I will explain the steps to pass the RGB image to the body joints, and then how we pass to the body joints to transfer the motion to the Blender model. So we'll have the two main modules. One is the pose estimation. So we note that our camera will have no depth information, it's only RGB image. And then we'll extract the 3D joints, and then from these 3D joints we'll transfer this motion to our 3D model. How we do this pose estimation? So the RGB image, first we will estimate the 2D joint positions, and then when we get these 2D joint positions, we'll have another network that will estimate the 3D joint positions. The first network to estimate the 2D joint coordinates, we use the alpha pose algorithm. This alpha pose is a top-down approach. Usually it's well-known top-down approaches. They first detect the body person, and this kind of system, sometimes they have the problem when there are many persons together or two persons are very close to each other. They have the problems detecting the person, but it's not our case because we'll assume the only one person in the scene. One advantage of this kind of method is they are very fast. They can run real time, even some 60 frames per second. And the skeleton retrieve is very similar to our skeleton model. This will facilitate to transfer the motion. And they report better performance than the state-of-the-art open pose algorithm. Other main advantage is we just can plug and play. We can just use the default weights that are given to us with the algorithm. Once we have the 2D joints, what we want to do is another network that transfer our 2D joints to the 3D joints. This we'll do with another network that it's very simple, and because the network it's very simple, it also makes it very, very fast and simple to train. The advantage of this is that we can customize our own data. So basically we can retrieve the 3D coordinates in the whole coordinate system that is already advantage for the Blender. And how we do this? For this we'll create a data set that it has already all the information in the whole coordinates that we will use in Blender. So for this we create a small data set, and we'll have the 6 different human models. We'll have the 54 actions, and from this we'll extract the 2D and 3D coordinates to train our network. So once we capture the 3D joint coordinates of the body from the RGB images, how we can transfer these points to our model, our model can move accordingly to that. So first we'll have our 3D model in a reference position. Then we have the detected 3D joint coordinates that we want to imitate. So we need to calculate how we need to rotate each one of the joints to get the desired position. So to do this, we'll calculate the rotations of all the joints one by one, but it's very important these rotations are calculated in hierarchical manner. So how we calculate each one of these rotations? So we have our model in the reference position, and we suppose we want to calculate the rotation of the joint that goes from O to Q. So because our model, 3D human model, is expressed in the local coordinate system of the bones, so we have one reference system, and then we'll have our detected 3D points that they will express in the whole coordinate system. So how we can make to calculate the rotation and take into account these two reference systems. So the first step is we need to align the two reference systems. So we'll align the local joint reference system to the whole coordinate system. And then we'll have, once we have the two joint vectors expressed in the same coordinate system, we can calculate which rotation we can apply. And then when we have calculated the rotation, because this rotation will be in the whole coordinate system, we need to transform again this rotation into the local joint coordinate system. So finally, we will show some results with the synthetic and the real data. First, with the data set we generate, we make some tests to check the two modules from the 2D joint detection and the 3D joint detection. From the 2D joint detection, we calculate the percentage of correct key points on the head on 0.5. This is a standard measure to detect the 2D joints. And we can observe that we have mainly the most problems when the person have the self-occlusions. It's performing some actions, it's occluding himself. Like, for example, bending, like when the person is bending, the hands are occluding the legs. In the case of the 3D module, what we detect is the worst performing actions. We have more problems when the actor is moving a lot, so we have more glitches in the 3D detections. Here is some video of the qualitative results. We have the Blender application, we have the model in the middle, and then we remove some of the sequence of the synthetic video performing some action. So in the left is the Blender model, and in the right is the synthetic sequence. And in similar manner, we do the same for the real sequence. So we have in the center the Blender model, and in the right now we have the video recorded with the webcam. So we can see mainly the action is quite well performed, but we have some problems sometimes with, for example, now in the leg of the person. Okay, thank you for your attention.